Hello everyone, welcome back to Mr. Lee's Math Class Videos. I'm Mr. Lee. This is Math 1316, Trigonometry. We're starting a new chapter. This is section 6.1 about radians. So everything we've done up to this point has been about angles and the relationships in triangles and straight lines that are across from them. But very often we're going to get into things that are dealing with circular motion and moving along the arcs of circles or finding the areas of sectors of a circle, things like that that are circular in nature. And we don't really have any way to handle those because the degrees don't reflect distances in that way, and they're not going to create right triangles for our trig functions to cover. So we're going to have a way of applying trig functions to a different version of angles that really measure lengths and areas and potentially other things, but those are the two things we'll primarily focus on. So the first thing to note is that if you think about the circumference of a circle, we know that a circle is 360 degrees, and we know that the formula for the circumference of a circle is 2 pi r, where r is the radius. If you solve this equation for the radius, you'll divide the 2 pi over to the other side and reduce to get the radius is equal to 180 degrees over pi. And since radius has a length, by converting our degrees to what we call radians, you can speak to lengths and areas in terms of their size based on the number of radians in question, or the size of the area or length relative to the radius itself. Which means if you're going from radians to degrees, you're going to convert the radians to degrees by multiplying by 180 and dividing by pi. But if you're going the other way, degrees to radians, you do the reciprocal. You divide by 180 and you multiply by pi. So we'll quickly cleave through some of these. If they're nice, one of the angles that's nice, it should work out to pretty nice fractions, but sometimes you'll have to toss them in the calculator. For example, A and B on each of these, you should be able to do without a calculator, but C on each of them will not be the same. So 45 degrees. This is a degree measurement, so we multiply it by pi over 180. The reason this helps us is the degrees divided by degrees will cancel. So we have really 45 over 180 pi, and this happens to reduce to 1/4 pi, or you can call it pi over 4. Either of these are acceptable. This is the most common version of how we would write the answer. And 270 is similar to 45. If you have one that's not nice, for example, 249.8 degrees, you're like, well, times pi over 180, that's difficult to handle. So this is a situation where you would just toss it into your calculator. So I would just toss the numbers into the calculator, but you also can get a decimal approximation of radians. So 249.8 divided by 180 times pi is to two decimal places, 4.36 radians. This is also in radians as a unit technically. So what they're really saying is that if you travel 45 degrees on a circle, which is halfway through the first quadrant, this angle or this length will be pi over 4 times the radius of your circle. If you go 249.8 degrees around a circle, it'll be that length around the circumference of the circle will be 4.36 radians. So depending on what your size of your radius is, it will change the actual length. But in this case, without knowing the radius, we can just refer to it to radians so that we know the relationship between the angle covered and the length in question. And I'll leave B for you to practice. And I'll, of course, put it on the key that I upload. Now, if you're going from radians to degrees to see how many radians, how that relates to the arc, you do the opposite. Instead of pi over 180, it's 180 over pi. So 9 pi over 4 times 180 over pi. And again, this is helpful because in this situation, your degrees is not going to have pi in it, so you want the pi to be able to cancel. 9 times 180, or you can do 180 over 4 first, which is what I'll do. Pi's cancel. This is really 9 times 180 over 4, which is 9 times 45. 9 times 45 is 405 degrees. Now, since it takes 2 pi to go around the circle, and this is bigger than 2 pi, you would expect it to be more than 1 time around the circle. So generally speaking, 360 degrees and 2 pi are equivalent in terms of radians and degrees, and so anything that's bigger than 2 pi is equivalent to an angle that's bigger than 360 degrees, or you're going more than 1 time around the circle. I'll leave negative 5 pi over 6 B for you to do as well, practice. And again, if it's one you toss in the calculator, you still do the same thing. 4.28 times 180 over pi. Again, this is going to require a decimal approximation. So 4.28 times 180 divided by pi is 245.23 degrees, which is kind of similar to this one. This 4.28 is a little bit less than the 4.36, and correspondingly, this angle is slightly smaller than the 249.8 from C on the first problem. Now this brings us to what becomes the most important thing that you ever learn or know in this class, and that's what we're going to talk about for the rest of this video. Many of you might have seen this at some point in time, but if not, this is the unit circle. The unit circle is the one whose radius is 1. If the radius is 1, then instead of talking about radians, since the radius is 1, that would be like multiplying whatever that arc length is by 1, so that's doing nothing. It creates the circle whose radius is 1 creates all of these values at various points, and these are the degree measurements and the equivalent radian measurement for each of these. So you're already familiar with the degrees. One thing to note is that the xy value on the unit circle is the cosine value of theta and the sine value of theta, or the cosine value of x and sine value of x. And what that means is it's theta if it's degrees, it's x if it's in radians. So if you see problems that ever mention theta, they want your answer in degrees. If they mention x inside the trig functions, they want your answer in radians. So we already know our cosine and sine values from the first quadrant. We've learned them, and really the respective ones over there. So this is showing you that for every angle that we have, there's an equivalent radian version of that angle on the unit circle whose radius is 1 that produces the same outputs for all of the trig functions. And that is super massive, so that even though we're learning a new system, all of the output values should be the same as you've seen them before. This also means that our 0, 90, 180, 270, and then back to 360 are every half pi, because if you take 2 pi and you divide it into 4 pieces, they'll be half a pi each. To notice reference angles, this is where radians are really helpful. The radians that all have the same reference angle all have the same denominator. So the pi over 6 is a 30-degree angle. 150 has a reference angle of 30. It is also a pi over 6, similar to 210 and 330, and that's true for all of the other ones as well, which means the radians behave within each other very, very consistently, which is actually really, really helpful for us. And there's also patterns for our numerator going around this circle. The numerator in the first quadrant is always 1 for all 3 of these. So our denominators are always 3, 4, or 6 if we're in a quadrant at one of our special angles. And the numerator is always 1 here. In the second quadrant, the numerator is always 1 less than the denominator, as you can see here. In the third quadrant, the numerator is always 1 more than the denominator. And in the fourth quadrant, it's always 1 less than double the denominator. And so that's a really easy way to remember what radian measurements are in what quadrants. The sooner you learn the values of the unit circle, or at least the values in the first quadrant and how to coordinate them with the other quadrants, the better you will be in this class, because it will not go away from beginning to end, and it will continue in other math classes from here, and we'll continue into problems in this section using radians in the next video.